Let's consider our last example for the week. Let's consider our last example before we move on and cover a couple of odds and ends regarding confidence intervals. In this case, I provided you with actual sample data rather than giving you the statistics that you need, as we did in example 1. Example 2 gives you the raw data and expects you to use some Excel functionality to compute the information that you need to use for later. Here's our setup. We're interested in the percentage of Endicott students that work more than 20 hours a week. To estimate this percentage, we collected survey responses to the left, where a yes indicates that that particular student does work more than 20 hours per week, whereas the no's would indicate that they do not. We want to use a confidence level of 98% to construct a confidence interval for the percentage of all Endicott students that work 20 plus hours per week. Now, fundamentally what we need to know here is our sample size and our sample percentage. But in order to determine our sample percentage, we need to know first how many people actually said yes in this sample survey. The other thing I want to point out here is that this sample percentage is very specific, right? We only want to compute the percentage that have a certain characteristic. In this case, it's people who work more than 20 hours a week, but we need to identify what type of response corresponds to that type of person. So in this case, we need to count up how many yeses are inside of our sample. So pause the video, see if you can remember how to do this. How do you go through a series of cells with text data and count up a particular type of response? See if you can do this on your own. All right, if you guessed COUNTIF, you're on the right track, A2 to A77. Remember, the criteria always has to be in quotes, and we need to make sure that we are counting up the yeses. So in this case, we have 7 people who said yes, but how many people in total are inside of this sample? It's a COUNTIF command. See if you can remember what your criteria should be. All right, COUNTIF A2 to A77. The criteria is putting a little asterisk inside of your quotes. This is a shortcut that just says count up any text, cells with any text in it. So we have 7 out of 76. In this case, to get p hat, we're going to take the number of people who said yes divided by the total. We're looking at about 9%. Okay, so far we've identified our confidence level. We're looking at our sample data. We've computed p hat. Our next step here is to find our critical value. Since we're working with a confidence interval for a population percentage, we should use our z critical value. So from a confidence level of 98%, we walk through our usual process. We find alpha, we divide alpha by 2, and then we use a dot inverse, in this case norm.s.inverse, with 1 minus alpha over 2 to its left to find our critical value. So here's our critical z-score, 2.33 if we round. In terms of our margin of error formula, it's our critical value times this square root term. So remember, we have p hat times 1 minus p hat. We divide that whole thing by n, and then we take the whole thing square rooted. In Excel, we start with the square root first. P hat times, make sure your 1 minus p hat is in parentheses, divide by your n, in this case 76, and then close out your square root function. To determine our margin of error, we take our critical value times the square root term, and this tells us that our margin of error is roughly 7.7%. So to get our confidence interval, we're going to take our p hat, we're going to subtract our margin of error for the left-hand bound. We'll take our p hat and we'll add our margin of error for the right-hand bound. And these are the upper and lower bounds for our confidence interval. So we can be, 98% confident that the true proportion in the population of Endicott students that work more than 20 hours a week is between, let's say, 1.5% and 16.9%. Keep in mind in Excel, if you wanted to modify any of these things, you're welcome to do that. You can change these to percentages, you can fix your own rounding, however you want to do this, but you do have access to that inside of Excel. Okay, let's recap. In this class, I want you to know how to do two types of confidence interval estimations. The first is for a population mean, where we do not assume that we know our population standard deviation. The second is the content that we just went over today, confidence intervals estimating a population percentage. Now, the processes are very similar to each other, but there are some tiny tweaks that makes one different from the other. One that comes to mind immediately is that when you're estimating a confidence interval for a population mean, right, in this case you should use a t-distribution, so t.inverse, to determine your critical value. For the confidence interval for a population percentage, you're going to use a z-distribution, so norm.s.inverse, to develop your critical value. All right. Inside of your Week 10 materials, you'll see an Excel workbook called W10 Practice. Inside of there, you have 4 different confidence interval examples. Some are going to be for population percentages, some are for population means. I recommend that you go through after watching these videos and try out these assignments and see if you can get the right answers. I'll be uploading solutions by the end of the week. Before we sign off for the week, I do want to just go over a couple of the assumptions that we need to make in order for our confidence intervals to be trusted. All right? So these probability models do make certain assumptions about the populations and about the sampling process that we have to make sure we as researchers can verify that's what's going on in order to trust the results of a confidence interval. So I want to go over those quickly so that you know what to look for as you're doing your own studies. First of all, for a confidence interval for a population mean, we're going to require that the sample is collected using a simple random sampling process. Okay, so the sample you get must be randomly selected from the population. You shouldn't be using a convenience sample. You shouldn't be using a volunteer response sample. You want this to be a simple random sampling process. Second, you have to be able to assume either your original population is normally distributed or we have a sample size of at least 30. Now, typically we don't know anything about our original population, so this usually just boils down to making sure that you have a sample size of at least 30 different pieces of information before you can trust the estimate given by the confidence interval. Keep in mind, this is the same requirement that we have for the central limit theorem. Right, and that's really no mistake. That's really no coincidence. Right. Essentially, what happens if you violate some of these things, you can still compute a confidence interval, but the success rate is not going to be what you think it is. So you'll compute an interval, but it won't have the same success rate that you might be expecting. Right. So if you set a confidence level of 95%, if all of these requirements hold, then 95% of the confidence intervals you could have generated would overlap with the mean. If you violate one of these, you may have a much lower success rate. So you may be more likely to generate a confidence interval that doesn't in fact include that population mean. So that's why we need to be careful. I'm going to show you this with an example when we're working with our confidence interval for a population proportion. All right, assumptions for our confidence interval for a population percentage. Once again, you have to make sure that your sample comes from a simple random sampling process. The other idea that is hopefully pretty straightforward here is that you have to make sure that your experiment or your survey that you're running satisfies the requirements of a binomial distribution. This population percentage can only relate to a group with a single characteristic. So you kind of have to break up your trials into 2 possible outcomes. They either have our characteristic or they don't, right? They answered yes or they don't. They had blue eyes or they don't. So we're modeling here the binomial distribution. A fixed number of independent trials with unchanging probability of success. This essentially just means that you've only collected a certain number of survey responses, so the fixed number is pretty easy to get. But you also want to make sure that you collect it in such a way that people's responses aren't affecting one another. So you may want to make the surveys anonymous. You may want to make sure that everyone turns things in separately without seeing what other people say. Remember, our analysis for this is a population percentage, so it's going to focus on only one type of response. Okay. The last requirement, and I'll show you what happens when we violate this, is inside of our sample we have at least 10 people saying yes and at least 10 people saying no. Right? So you have at least 10 people in the positive characteristic and 10 people in the negative characteristic. Right? So 10 people with blue eyes, 10 people without blue eyes, etc. Right? Now, if we end up violating this, which typically happens when we have a small sample size and a very small probability of, or a small population percentage, essentially what happens is, again, our confidence level is what suffers, right? So the success rate of this process is much worse than we were expecting it to be. So I want to walk through an example of that using a simulation where you can see where if you violate some of these assumptions, that success rate basically tanks. Okay, here's our familiar simulator working with confidence intervals for a population proportion. Now in this case, I've set it up so that I'm going to violate one of my assumptions. In particular, the assumption that I'm going to violate is that I have at least 10 yeses and at least 10 nos inside of the sample. Okay? Now the way I do this is by setting the population proportion to be very small. So in this case I have 10% of the population actually would say yes to my survey question, and I'm only going to collect a sample size of 15. Now you'll notice you can still collect samples and it will still compute a confidence interval. In particular, the confidence intervals the simulator computes is at a confidence level of 95%. So in theory, what I'm expecting as a researcher is that 95% of the confidence intervals that I generate, and we're going to simulate a bunch of these in a second, 95% of them should overlap with this 10% population proportion. But what we'll see is by violating this assumption, at least 10 yeses, at least 10 nos, by violating that assumption, we end up getting a much worse success rate than what we were expecting by the confidence level we set. So let's collect a whole bunch of examples here. So after collecting about maybe 600 different confidence intervals based on random samples from this population, we can see that our success rate's actually 78%. We're expecting it to be 95%. That's the confidence level I set. But what we're getting out of the simulation is something much lower. And this is what happens when we end up violating some of these assumptions. We end up having a true success rate for the process being much lower than the confidence level we set. And this gives us the disparity between what the researchers are thinking as the success rate of their process and what their actual success rate ends up being. Okay? So if I violate one of these assumptions, I can't assume that I can't be anymore 95% confident that my confidence interval overlaps with P. My success rate's probably much less. And this is why, if you cannot be sure that you've met the requirements of the confidence interval, you should not trust the results. You cannot trust that your population parameter is going to be inside the confidence interval you computed. Great work this week. We learned about confidence intervals, and in particular, there's two different types of confidence intervals that you should know how to compute at this point and interpret. Confidence intervals for a population mean and confidence intervals for a population proportion. Remember, in your Week 10 materials, there's 4 extra practice problems that you should definitely use as a self-testing opportunity. Go in there, attempt these, see if you have questions. I'll be posting solutions later. If you do have questions, please post something in Piazza or come to some of the live office hours to get the help that you need. I'm here to help you guys, and I hope that this week went well for you. Thanks.